So today we're starting our third week of lectures, and today, well, this first one is just going to be on the Doppler effect, namely the relativistic Doppler effect. So just to review, we're going to keep reviewing this stuff. Here was our Lorentz transformations from Mary to Frank, Frank to Mary. Here was our transformations for the velocity. We said that what we came out this equation, and that is the time for the proper time. If you measure the event at the same location, you're the proper time. A moving clock, that is a moving clock or a moving observer, will always measure the time a little bit longer by this amount right here. And we called that time dilation, and we called this length contraction right here, where again the L naught was the proper length, the length that isn't moving relative to u. And we said for light, V is c, and time would be infinite, which means time doesn't exist, and length would be 0, so space doesn't exist. The universe would have no dimension, and the photon or the light would be everywhere at one spot. Okay, so I just wanted to review that. So now what we're going to be talking about is the Doppler effect. And so just to remind you what the Doppler effect is, it's usually you have some sort of a transmitter, a frequency right here. Let me just say it's a speaker. Let's just say it's sound right here. It emits some sound right there. And then out here we have some receiver, which could be your ear. There's your ear. And if this moves toward you or you move toward the speaker, you're going to hear a slightly different frequency. I'm not going to derive this because this is the non-relativistic. This is sound. This is where there is a special frame. It's still there. But the frequency, this is the receiver over here. Receiver. And this is the transmitter. But the equation for it is the frequency that you receive, or receiver, is equal to the frequency of the transmitter times some factor right there. And that factor is the speed of sound. And then this one, it's plus or minus the speed of the receiver, depending on which way he's going, speed of the receiver, all divided by the speed of the sound, plus or minus the speed of the transmitter. Now, they might do this in one of the other physics classes right here. And if the plus and minus depend on who's moving which way. If this is moving in that direction right here, then you use the plus right here. That's for the, if the receiver is moving this way, then that's the plus. If he's moving this way, then that down here is the minus right here. And so we can see that, let's just say that this is at rest, and he's running towards it right here. Well, if he's at rest, this is 0, and this is a plus. Now let's look at the other case. What if he's not moving, and this is moving towards him? Well, then this is 0, and this is minus. And those are completely different equations. So you can tell who's moving right here. That is, this moving versus this moving, they can tell who's moving because they don't get the same frequency received right here. So there's a special frame right here. But for our case, for the relativistic, where this is light and light coming this way, we shouldn't get this. We should get symmetrical behavior right here. Okay, so let's look at it for symmetrical behavior. I'm not going to look at this. Well, okay, so now, when we look at it, now what we're going to do is we're going to send light out, and we're going to have an eyeball here instead, right? Okay, so how do we do this? Well, let's look at our XCT diagram again, right here. Minkowski diagram. We had our x here, and we have our CT. Now we're going to have, and then we have our CT prime, and we have our x prime. So this will be, there's our Mary's frame right there, Mary's x prime. Okay, so what are we going to have? We're going to have Frank over here. There's Frank. Shining some light. And out here, we're going to have, it doesn't have to be Mary. Maybe we'll just make that Mark. He's the receiver. He's going that way. So Frank is the transmitter. He's sending out the light. And Mark is the receiver. He's going to detect the light. Remember, he's moving that direction. He's on the red coordinate system. Now, instead of using a frequency here, we could just use a frequency. We could, instead, it'd probably be a little easier if he just sends pulses. And because anything that pulses has a frequency right here. And we can see, we know that the frequency is equal to 1 over the period. So he's just going to send out a flash every period. And he's going to detect flash at some other period, and we'll work with periods, and then at the end we'll flip it to get frequencies. Right here. Okay, so we need Mark out there. Where's Mark? Mark is just going along this line right here, so he's out here someplace. So there's Mark's line. So this is Mark right here. And if we go all the way back, let's just say it goes to, I'll just call this x sub naught. Doesn't matter. It shouldn't matter in this problem right here. Okay, so now what's going to happen? Well, Frank's going to send out a pulse. We know the pulse goes at 45 degrees, so it's going to head up this way right here. So it heads up. There's the pulse right there. And he's going to see that pulse. Then Mark is going to wait a period, one period, and then send another one. So this distance here must be c times the period between, I'll use that little fancy t, and then he's going to send another pulse. So it's just going up parallel to this other one. There it is, right there. And so he detects it here, and then he detects it up there. Okay, so this point right here, I guess we could call it x1 CT1. CT1. And we could call this point x2 CT2. And that's in Frank's frame. In Mary's frame, or Mark's, Mark's, it's the same. In that frame, we use the prime, right? This would be x2 prime CT2 prime. This one down here would be x1 prime CT1 prime. Okay. So what we want to do is, in this, we want to find the x1 and the t1s, x2 and t2, and then apply the transformation to find the red ones right here. Okay. So we need the equation of these lines, just like we did before. Well, what's the equation of this line right here? Remember, the equation of this line was x equals vt. We did that before. We said the equation of this line was x equals ct. X equals ct. And this line was x equals vt. And this one is just shift over by x sub naught. So the equation of this line must be vt plus x sub naught. So this is x is equal to vt plus x sub naught. That's the equation of that line. And then we need the equation of this other green line right here. Again, we can use the y equals mx plus b, y equals mx plus b. We know the y, well, we know the y is just ct. And that equals m. The slope of this is 1. It's light. So that's 1 times x. So that's just x plus my y-intercept. My y-intercept is just c tau. So x is just ct minus c tau. So this is x is equal to ct minus c tau, right there. So we have the equation of this, we have the equation of that, we have the equations. We can find those values right there. Okay, so first, let's just set this equation equal to that equation. And that would be at x1. So that would mean that ct1 should equal vt1 plus x sub naught. vt1 plus x sub naught. Okay, well, let's do the same thing for this. Let's set those two equal, and that's at 0.2. So that would mean if we set these two x's again together, at this point at t2, you get ct2 minus c tau. We got ct2 minus c tau. And that equals the equation of this one at t2. That would be vt2 plus x sub naught equals vt2 plus x sub naught. Okay, I don't know x sub naught. It should just drop out, so I'm going to subtract these two equations right here. If we subtract these two equations, you can see that these two will drop out, and we get this minus that, so we get ct2 minus c tau minus ct1 equals this minus that, which is I can factor out the v, and that's t2 minus t1. Okay, well, let's bring these two terms and factor out the c out of these two. So we got c t2 minus t1. Then we still have this term, minus c tau equals v t2 minus t1. Now we'll bring that term on that side, bring this term back, and factor it out, these two together. So we'd end up with t2 minus t1, and now this is going to just be c minus v, and that equals c tau. I move to that side, c tau. And so I can solve for t2 minus t1. t2 minus t1 is equal to c tau all over c minus v. So we've got that so far, right there. Now I'd like to find x2 minus x1 right here. Well, you notice this equation right there, the equation right there, this is just vt1 plus x sub naught is just x1 right here. So right there, that's just x1, so I could have just set this equal to x1. And when t equals t2, this equation is just x2. So we can also set this equal to x2. And I'm going to subtract those two because I want x2 minus x1. So if I subtract these two, just the right side, we get x2 minus x1. And that equals this minus this. The x sub naughts drop out, and we can factor out the v, and we get t2 minus t1. But I have t2 minus t1, so I'm just going to plug that back down into here. So x2 minus x1 is just v times this. So it's v c tau all over c minus v. Okay, so I've got t2 minus t1, and I've got x2 minus x1 right here. So what do we want to find? We now want to switch this thing over and find tau prime. Remember, t2 minus t1 is just the time between sending the flashes. So from Frank's point of view, that's just tau right there. And T2 prime minus T1 prime would be the period between receiving the flashes in Mark's frame right here. So that would be tau prime right here. That's what I want to find, because if I flip that, that's the frequency that he sees. Okay, so let's solve for tau prime right here, which is T2 prime minus T1 prime. So tau prime, we'll put it up here. Tau prime is equal to T2 prime minus T1 prime, which is equal to, we'll just plug in our primes right there. We'll plug in that equation for 2 minus 1. So for 2, that would be T2 minus x2v over c squared divided by the square root of 1 minus v squared over c squared minus, and then do it with 1, T1 minus x1 v over c squared divided by the square root of 1 minus v squared over c squared. Okay, so we can pull out our common denominator, and we're left with T2 minus T1, which we already got, which is right here. So I'm going to plug that in for the T2 minus T1. So we get C tau all over C minus V. Okay, and then I'm going to factor out the minus V over C squared. It's in both terms. So we got minus V over C squared. And you're left with an x2 minus an x1. x2 minus x1 is right here. So we'll plug that in for x2 minus x1, which means we get V, C tau, all over C minus V. And then we have our common denominator right there. The square root of 1 minus V squared over C squared. Okay, well, let's, I'm going to take, well, what do we have? We have a C minus V in both terms right here. I could actually put it down on this level right here. So I don't need a compound fraction. So we got C tau minus, and then I'm just going to multiply this and put it in the numerator up here. So that's V squared over C minus C tau all over, well, I'll just leave it the way it is right here. It's going to be V squared, V squared over C. C over C squared is C. V squared tau all over C minus V times this. So we got a C minus V, and then we got a square root of 1 minus V squared over C squared. I think I'm going to put that C back in here. We'll put the C back in, and we'll bring the C back up to the top, because I see that if I pull out the C here and the tau, we get C tau, and we're left with just 1 minus V squared over C squared, which is good because that's what I have down below. I have a 1 minus V squared over C squared divided by C minus V, square root of 1 minus V squared over C squared. Okay, so now I can, this divided by that just gives me a square root in the top. So I end up with a square root of 1 minus V squared over C squared in the numerator. I'm going to take this C and bring it all the way down below here. So I still have the tau. If I take that all the way down below, this is 1 minus V over C. So I end up with 1 minus V over C. Okay, and then I think we can simplify that more because this is the difference of two squares. So I can simplify that to 1 minus v over c, 1 plus v over c. 1 minus v over c, 1 plus v over c, all over 1 minus v over c. Well, this and that just gives me a square root of that in the bottom. So we get tau prime is equal to tau times the square root of 1 plus v over c divided by 1 minus v over c. 1 plus v over c divided by 1 minus v over c. And now if I wanted to get the Doppler frequencies, I just flip everything here because the flipping of this goes to frequencies right here. So this would be f prime, which is really the receiver. Remember, that's Mark. This is the receiver. And that equals this flipped would just be f, which is the frequency of the transmitter, which is Fred. Transmitter. This is Fred right there. And then we have to flip this, which is the square root of 1 minus v over c. Square root of 1 minus v over c all over 1 plus v over c. So that is the relativistic Doppler effect when, remember, Mark's moving away. If Mark moves away, then you noticed here, this number is getting smaller and this number is getting bigger, which means the whole thing gets smaller right here, which means this frequency is getting lower right here. So it's going more toward the red. The red has the lowest frequency of light, and so they call this redshift. Redshift. Now, if Mark was going in the other direction, then you just change the sign of the V, and that would have been plus, and that would have been minus, and it would have been larger, and you would have called that blue shift. Right. So that's red shift and blue shift. Now, you noticed if we were to give this, if we were to switch this thing around so that we looked at it so that Mark was the transmitter and Frank was the receiver, we worked from Mark's point of view. What do? Every place you see a receiver, you change it to a transmitter, and you change the sign of the V right here, just like we did before. So this would be, from Mark's point of view, it would be, you'd say the frequency prime of the transmitter equals, this is the receiver. Let's leave that even now. This is the F of the receiver. And then you change the sign of the V, which is 1 plus V over C divided by 1 minus V over C. And then you, again, what we want to find is the receiver. What does Frank see? This is what Frank sees. F of the receiver is F of the transmitter times the square root. Bringing this over, it's 1 minus V over C divided by 1 plus V over C. You notice it's the same equation right here. They're symmetric right here. They should be symmetric to each other. Okay, well, this is again called the relativistic Doppler effect when they're moving away right there. Now, in 1929, Edwin Hubble, using the Hooker telescope on Mount Wilson here, just down near Pasadena, it's the mountain just above Pasadena right there. Looking at galaxies, he noticed that if you plot out, this is the distance to galaxies, distance to galaxies, and this is their radial velocity, how fast they're moving away. When we talk about this, we mean radial velocity. This is their radial velocity. And you do it for different galaxies. You might say, how do you get the radial velocity? Well, from this formula right here. You can look at you're the receiver right here, and the transmitter is the star right here, and it's moving away, and we look at a specific frequency right here. We'll look at maybe hydrogen. We'll see later that hydrogen gives out certain frequencies of optical light, and a bright red one would be something called an H-alpha line right there. It's a bright line in hydrogen. It has a certain frequency. Well, you know what the transmission frequency of this is, and then you can get what frequency you see it at. If you know these two frequencies, you can get the velocity, and that's what we're getting. We're plotting out the velocity. Now, how do you get the distance to a galaxy right here? Well, in certain galaxies, at least nearby ones, there are stars that their brightness kind of goes up and down right here. They pulsate right here. And the period of pulsation is related to the brightness of the star. And so you can easily get the period of pulsation just watching it getting brighter and darker. So you can get the actual brightness of the star, and then you can see how bright it appears to be. If you know how bright it really is and how bright it appears to be, you know the distance. And so if you plot those two parameters, you get something like this, which looks like a straight line right here, which means that if you fit that to a straight line right there, if it goes right through the origin, we know what the equation of a straight line is through the origin. It's y equals mx right here, or y, which is velocity, equals the slope times the x value. Well, the x is d, so they called the slope of this, the slope, h, for the Hubble constant. So it's the equation of this is v equals hd right there. And it's important to get this constant right here because the age of the universe, period of the age of universe is like 1 over h right here. Well, when Hubble did this, he couldn't measure the slope very well. First of all, you had big error bars. When you got big error bars, actually I shouldn't say vertical error bars, they should be horizontal error bars because you can get the velocity quite well, but what you can't get is the distance very good because you can't see out to far galaxies to see these variable stars, so there's big error bars this way, which means it's hard to get a good slope right here. And before the Hubble telescope went up, this slope was so bad that the age of the universe was somewhere between 10 to 20 billion years old. Billion years. Which is like it's a big error between 20. But when the Hubble telescope went up, they were able to see these variable stars much further out, able to bring these way down. And now the universe is somewhere like 13.8 billion years old right here. Might even be no more accurate than that. So they've really got this down right here. You'll notice right here that if I keep following this, eventually this velocity is going to exceed the speed of light, because you got a limit right there. This is the speed of light right there. Well, can I just keep going out? Are galaxies far enough going to be going faster than the speed of light? And the answer is yes, right here. They are going to be going faster than the speed of light. Does that mean that you have problems about going backwards in time like we said before? No. You could determine what this maximum distance is because you can plug in the speed of light there and solve for d right there. The best value of h that we have for the rate at which everything is going outward from each other, everything expands at about 70 kilometers per second for every 4 million light years. 4 times 10 to the 6 light years. So if you go out 4 million light years, galaxies are going 70 kilometers per second. If you go out double that, they're going 140 kilometers per second. If you go out triple, they're going 210, and so on, right here. So this is our best value, pretty much, of the Hubble constant, right there. But how can you go faster than the speed of light, right there? Well, the problem is this Doppler shift isn't due to the velocity of the object. It's actually due to the velocity of space. When you get way out there, remember, general relativity takes over, and general relativity says space is a quite dynamic thing right here. And so space is what's expanding, not the objects. And one way of looking at it, suppose we have, let's just look in one dimension right here. We have a bunch of galaxies. Let me just place them at nice uniform spots right here. Here's a coordinate system. Let's say we've got here's us, the US. And I'm just going to label this coordinate system. Here's 2, 3, 4, 5. Let's say there's the galaxy at each one of these locations right there. And so we just keep going on right there. There's a galaxy at these are each galaxies right here. And this is now, right here. If we were to come in, so this is now. If we talk about in the future or later, first of all, let me just say the space between all these is A, and so on, all the way down. In the future, it's going to look more like, and so on. So again, my coordinate system, this is still my coordinate system, that's still 0 on my coordinate, that's still 1, 2, 3, 4, and this galaxy is here, and he's still at x equal 1. He hasn't changed, but A has changed, the space between them. So this is A. We could say way out there, you're at x right here. Way out there, about further, you're out at x right there. So the distance to a galaxy, let's say if we wanted to get the distance to this galaxy, wouldn't it really just be 5 A's? 1, 2, 3, 4, 5 A's. Or the distance out to there would be x A's. So we could say the distance is equal to x times A. But in this, it's kind of strange that in this formula right here, x is the constant right there. X isn't changing. This galaxy stays at position 1. It's the A that's changing. A is the one that's a function of time right here. And so what do we call this A? We call this A the scale factor. Scale factor. So we call that A the scale factor. And so what's happening is this just space is. Now, if the star is moving relative to space, then he won't be at 1. He might be at 1.0001 or something. But that's a very small motion within relative to space. This is just the expansion of space, and there's nothing that says that these can't exceed the speed of light. Space can expand faster than the speed of light right here. Now, I should say that when we defined this Doppler effect right here, and we defined what we called the redshift, they actually give it a symbol here, redshift. They actually called it Z right here. And the equation really is 1 plus Z is actually equal to the frequency transmitted divided by the frequency received. So it's really defined as the frequency transmitted divided by the frequency received. Well, what is the frequency transmitted divided? If I bring this down below, I have to take this and bring it to the other side and flip it. It's the square root of 1 plus V over C. So that's equal to the square root of 1 plus V over C divided by 1 minus V over C. And you can see that this number is bigger than 1 right there. Now you might say, why do they make it 1 plus? Well, you can see if v is 0, you get 1, which means z equals 0 if it's not moving. That's why they put the 1 plus right there. The bigger v is, the bigger z is right here. Now the furthest galaxy they know is a z of about 11. So z is about 11. Well, that would mean, if you plug that in here, that means this is 12. That means the frequency shifted by a factor of 12. So astronomers like that because they're looking at frequencies and they just say, well, this frequency is shifted by a factor of 12. That must mean that the redshift is 11. They just subtract 1 off of it right there. Well, we can define it also down here, this 1 plus z here. Again, it's a redshift right here. I guess we could call it a cosmological redshift. Instead of being the ratio of the frequencies, this is the ratio of the scale factors. It's a now. They actually go over a to the past right here. A in the past. Right there. So this is the way it should be in cosmological right here. So this is, again, the redshift right here. So that galaxy we saw, which was 11, it really should use this formula because it was actually space that expanded right there. Within our galaxy, you can use this all you want right here. But once you start talking about way out there, then you're going to have to use the expansion of space right there. Now, if you go back as far as possible, all the way back to the cosmic microwave background radiation, right there, it's the smoke they see left over from the Big Bang. They've actually taken a picture of it. That was when the universe was about 4,000 degrees Kelvin. It is now cooled, we'll see later, that it's cooled down to about 4 degrees Kelvin. So the universe is cooled about 1,000 times since this cosmic background radiation picture is, which we'll come back to again later, which means the universe expanded by about a factor of 1,000. So this ratio right here is about 1,000. And that's when the universe was pretty young. It's when the universe was a couple 100,000 years old, right there. Now, I should say, what does this A look like? These A's are not constant. Remember, they're a function of time. And so if we were to plot out that A as a function of time, well, I'm not going to derive it here, but when the universe was very young, it was dominated by radiation. If the universe is dominated by light, radiation, then this goes as a square root. So A goes as some constant times the square root of t. So this is A versus t. It goes as like the square root right there. And this, as long as the universe is dominated by radiation, this is the way the expansion of space goes. And that only happened for about 10,000 years, so maybe around 10,000 years. And then matter became dominated right here. Mass became more dominant than the light. And then it went as alpha t to a different power, 2/3. 2/3 goes up a little bit more. And this would have been, this is dominated by radiation. Here you're dominated by matter. And this continued on until about a few billion years old. So this is, say, 2 billion years. And then dark energy. The universe got big enough that empty space is actually a repulsive force. And the more space you get, even the more force you get. And this thing now takes off exponentially, like e to the alpha t, right there. And so right now, we're at 13.8 billion. We're out here someplace. We're in this rapid, we're expanding right here. This universe is is accelerating outward right here, just due to this something called dark energy right there. Okay, so there is, so when you're looking at really large scales, you can't use this right here. You got to use this right here. And I should say there's one more type of redshift, which is gravitational redshift. If you have a star and light leaves the star, it has to fight to leave the star. If you're going to fight, it has to lose energy. Just like throwing this ball up, it loses energy. Well, if light loses energy, it doesn't lose speed. The speed of light is always the same. What does it lose? It loses frequency right there. And so when light leaves, even the Earth, it loses a little bit of frequency when it leaves. You might say, well, it's hard to notice. They've measured it. But what happens if you're leaving a black hole right here? This could be a black hole, and you're not coming from the surface. You're coming from right on the edge of the horizon where you can get out. You can't get out of there. But it can be shifted by quite a bit right here. And so that, for gravitational redshift, it's 1 plus z equals 1 all over the square root of 1 minus 2 gm over r, where r is where it took off. This is the mass. There's the gravitational constant. And you can see that this number is less than 1, which means this number is bigger than 1, and this tells you how much the frequency shifts a little bit right here. Remember, you always want z to be redshifted to be bigger than 1. So they call this the gravitational redshift. So don't get fooled just because you see something like some frequency redshift. It could be due to a star, black hole. It could be, if it's way out on the edge of the universe, it could just be to the expansion of space. But nearby, if you're going to use it on the Earth or something right here, then you use this if it's just a velocity relative to space. Okay, so there's the Doppler effect. Okay. Oh, one last thing. You notice when you see a red light right here, this is a red light. Red light has a long wavelength. Green, sorry, I should actually put them in red and green. Red has a long wavelength. Green has a much shorter wavelength. So what happens if you run at a red light? If you run at a red light fast enough, you can squeeze the wave to make it green. So just in case you're sick of those red lights all the time in the traffic, just remember, if you go fast enough towards it, you can shift the frequency to the green light and just keep going. You won't get a ticket for a red light, running a red light. You might get one for speeding, though. Okay.